AP Chemistry students. This is Mrs. Hanson. I'm doing this video, but Ms. Schneider's going to be doing a bunch of them too. So, hopefully this goes all right. My goal is to keep it brief. Please remember that you need to pause it so you can write things down. All right, so today we're going to discuss kinetic molecular theory of gases. The whole idea here is the word kinetic means movement. So today we're going to talk about how gaseous molecules move. Okay, first of all, there's four big assumptions that we want to keep in mind. The first one, I'm going to start with the simplest one, is this guy, motion. Well, you know what? If you look back at this old gas law simulation that you looked at in CP Chem, this guy right here, notice the gas particles are in constant random motion. Okay, so we knew that. All right, this one. You may not have ever thought about this one. Oops, I didn't mean to move all that. Let's fix that. This guy, particle volume. It says gas particles have negligible, that's a hard word to say, or no volume. What that means is that when you look back at our sample, you know what? Gas is really spread out, right? So when you look at our sample, we assume that, okay, the volume of the container is 1 liter. We don't really care about the fact that the gas particles themselves actually take up volume. We just assume they don't take up any volume. So when we say Pivnert, oh, the volume's 1 liter, okay, we assume that that's empty space. Okay, but the gas particles themselves, we assume that they're so small, their volume is so small compared to all the empty space in the size of the container that the gas particles themselves have no volume. Okay, so I hope that makes sense. All right, this guy right here, attractive forces. You know what? This by far is the most important one, I would say. Okay, we assume that gas particles virtually exert no attractive forces with each other. This is a super important one. So when you look at a gas sample, okay, what you notice is that, you know what? The gas particles really don't pay attention to each other. Okay, they don't have attractive forces for each other. This alone is probably what most dramatically distinguishes gases from solids and liquids. Solids and liquids definitely kind of hold on to each other. Gases, when you release a gas into a volume, they just totally spread out to fill the container, pay no attention to each other. Okay, and finally, the last one is about collisions. We assume that when gas particles collide, which they do a lot, and remember that collisions are what causes pressure, when gas particles collide, we assume that those collisions are perfectly elastic. Okay, and what that means is that when the gas particles collide, we assume that they don't lose any energy. So if it was a super bouncy ball and the collisions were 100% elastic, that super bouncy ball would bounce forever. That's right. So we assume gas particles are that way too. Okay, now that's not entirely true, but we'll talk about that in a minute. Okay, we have to assume that gas particle collisions are 100% elastic. Otherwise, you know what? Eventually all the particles of air would be resting on the ground, and you know what? That would make it really difficult to breathe because all the air particles would lose their energy. Okay, so these are four really big ideas of kinetic molecular theory. The other one is about kinetic energy. I'll put this guy away for a little bit. So kinetic energy is basically measured by temperature. Okay, so the average kinetic energy of gas particles is proportional to temperature. Now, any two gases that are at the same temperature, what does that mean? If they're at the same temperature, they must have the same average kinetic energy. So you guys probably remember that from CP Chem. Okay, now these ideas related to kinetic molecular theory, you should be able to think about how particles move to explain all the gas laws and equations and everything we've been doing. So I suggest that you refer to these pages and just read through it and make sure that any gas phenomena that we could ask you to explain, that you could explain it in terms of attractive forces and motion and collisions and volume and all those things and kinetic energy. Okay, but we'll practice that a little bit more in class. Let's talk a little bit more about kinetic energy. So the formula for kinetic energy that you might remember from physical science is kinetic energy is 1/2 mv squared. Okay, now V actually stands for the mean squared velocity. Okay, velocity. So velocity and speed are kind of used interchangeably when we're talking about molecules. Okay, so the basic idea is that this is the average, okay, of the square, and that's where the little square comes from, of the speeds of all the molecules. Okay, sometimes you guys might see that not represented with a V for velocity, but actually a little U, and that's okay too. Okay, but for our purposes, we'll go with the V. Now, kinetic energy actually depends on two factors, as you see right here, this guy and this guy. So it depends on both the mass and the velocity of the particles. Okay, so the average kinetic energy of molecules is the same at a constant temperature. Okay, now that's the average, right? So let's go back to our little simulation. If you look at all these gas particles, you know, are they always moving exactly the same speed? I don't know if you pay attention to that one that's being tracked. Let's watch it for a second. Oops, off the chart. Oh, it went fast. It slowed down. Went fast, 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 fast. Slowed down. So at any one instance, all these particles are going very different speeds, but the average speed of all these particles is the same, okay, or stays constant. Okay, so why or why not? So the idea is that some are moving fast, some are moving slow, but the average, the key here is the average speed stays constant. Okay, now believe it or not, this very funny looking graph represents exactly that point. Okay, now this graph, you probably haven't seen one like it, but basically this one's based on temperature. So the one thing that might jump out to you is, let's take a look at the axes. So this one, we have number of molecules. So if you have a sample of 1,000 molecules, okay, and this is speed, we're going to map the speed each of those 1,000 gaseous molecules are going, okay? So the one thing you might notice is as temperature increases, so as you go from 0 to 1,000 to 2,000, what do you notice is happening to the molecular speed? Okay, well, you notice that from the red to the green to the blue, basically the curve just kind of keeps shifting to the right. So molecular speed increases, okay, which hopefully is exactly what you'd expect. Okay, if the particles have more kinetic energy, then they're going to be moving faster. Okay, now what's kind of weird about this graph is that you notice that, it's really tall here, and then it flattens out, and it flattens out. Okay, well, just keep in mind that what's most important here is what's the average speed. Okay, so if you look at this red line, okay, let's say we got those 1,000 particles. This is how they're distributed. So some are going slow, like we saw in the little simulation, and some are going really fast. Okay, but the key is right here at the top of the hill, that's the average speed of those particular molecules in that sample. Okay, and then for if we raise the temperature to 1,000 degrees, well, you know what? Some particles are going slow, some particles are going fast, but the average is right at the top of the hill. So most of the gas particles are going this speed, okay, because that's number of molecules on this side. Okay, and then same thing with the 2,000 degrees Celsius. Okay, so now my average is all the way up here. So as temperature increases, the average molecular speed definitely increases. Okay, now why does it, start off like sort of pointy up here, like a tall curve, and then it kind of flattens out, flattens out? Well, if you think about it, you know what? When you're going from, I don't know, let's say you're in your subdivision, 0 to 25 degrees, the speed limit's 25 degrees. Well, there's not that much different speeds that you see at that slow temperature, okay? But if you're on like the Autobahn and people are going like 110 miles per hour, well, there's a lot of possible speeds that people could be going. They could be going 0, they could be going 20, they could be going 50, they could be going 70, they could be going 100, they could be going 120, etc. So you have a lot more possible speeds, okay, when you raise the temperature. So that's why you got some going slow, some going a little faster, some going a little faster, and so on and so forth. So as temperature increases, molecular speed becomes more variable. Okay, that means that curve kind of spreads out. Why is that? So this is basically our general idea. At increased temperature, there are more possible speeds. So the curve is more spread out. Okay, so I hope that makes sense. We're going to talk a little bit more about this curve down the line. Okay, but the bottom line is the average speed is what's really important. Okay, and that in general, as temperature increases, molecular speed increases. Okay, does that make sense? Yes, Miss Hanson, it does. Okay, good. So here's our next question. So let's say we're talking about two different gases, and they're at the same temperature. Now, because they're at the same temperature, they should have the same what? The same kinetic energy. Remember, temperature measures kinetic energy. But do their molecules necessarily travel at the same speed? Okay, and you guys probably remember this, maybe from CP Chem, I hope. So if you guys go back to looking at our little simulation, I hope I can get to it. Come on, there we go. Okay, I'm going to go ahead and turn this off. And you know what? I'm going to add another gas particle. So what do you guys notice? Who's traveling faster? Well, I think it's pretty obvious that the little green guys are traveling a lot faster. The blue guys, they're really big, so they travel slow. This is also illustrated with the Maxwell distribution graph that you see. Okay, the blue guys traveling a little slower, their average velocity is here, whereas the green guy's average velocity is here. Okay, so do you guys remember that? Good. So basically, the heavier the gas, the higher its mass. Well, in order for the kinetic energy to stay the same at that constant temperature, then the velocity must travel slower. So heavy gas means slow velocity. Okay? You guys might remember this in this demonstration that we did that a long time ago that had ammonia at one side, NH3, and had HCl at the other side. okay? And they were both gases, and they were on Q-tips, and you know what? It was like a molecular race. The gases were released, and they traveled, and they traveled, and they traveled through this tube, and they met somewhere in the middle. Well, as it turns out, they met right about here, which what's that tell us? Which gas is actually traveling faster? Well, this guy went from here to here. It traveled a further distance, so it would travel faster. Well, ammonia's molar mass, let's see, 14, 15, 16, 17 is about 17 grams per mole, versus HCl's molar mass, let's see, 35.45, so plus another hydrogen is about 36.45 grams per mole. So the smaller molecules, the lighter molecules, the lower molar mass, those guys were able to travel faster. But please remember that since the two gases were at the same temperature, they have the same kinetic energy. All right, so there's a term for this, and it is called gaseous diffusion. Sorry about my voice getting squeaky there. Gaseous diffusion. All right, so of course, this is AP Chem, so we're going to have to quantify this, okay? First of all, if you wanted to, and you probably don't, you could calculate the actual speed that gas particles travel. You could use this formula, and it's kind of a weird looking formula, and if you refer to page 219 to 222, it explains exactly how it got derived. You use a little bit of Pivner, and you use some physics, and you combine a couple equations, and you could solve this. The weird thing is it's a molar mass has to be in kilograms, and R is not the normal R, but a different R. But nonetheless, and you could solve for the actual speed that gas particles travel. We are not going to do this, but I will tell you that gas particles travel really fast. Their speed is usually on the order of 600 to 1600 meters per second, which is actually about 1300 to 4000 miles per hour. So that's really fast. But the thing is you know what, in real life, gases never travel that fast. Why? Because in most scenarios, when you're dealing with gases, you're also dealing with air. So if I release a gas on one corner of the room and it has to battle all the air particles that are out there, you know what, it's going to create a lot of interference. So these are the predicted values, but truth be told, because of collisions with air particles, those speeds, you never really see them, okay, unless you have some kind of artificial, like, vacuum type situation, okay? So we're not going to worry too much about that, but what we are going to worry about is something called Graham's Law. I would say for today, this is probably the most important thing you're going to learn. Graham's law mathematically relates basically how fast the velocity of the gas particle to its molar mass. And it looks a little something like this. So rate is another way of saying velocity. It's kind of like how many meters per second you travel. So if you take the rate of one gas, okay, and we're going to compare it to the rate of the other gas, okay, well, they're related by how heavy or light they are. Okay, but it's an inverse relationship, right? So that's what's kind of constructed with this formula. Basically what you're saying is if this is the rate of gas 1, then the square root of its molar mass is on the bottom because they're inversely related. Gotta remember that. So rate 1 goes with molar mass 1. Rate 2 goes with molar mass 2. Inverse relationship, so that's why the formula is kind of flipped like that. And don't forget that its kinetic energy is 1/2 mv squared, so that's why you got the square root relationship going on there too. Okay, so let's go ahead and practice that. So here's our little question. Now, folks, this is where you want to read through the question. You want to do it yourself, okay? And then, when you got yourself an answer, then you resume this video to see if you got the answer right, okay? So right now, go ahead and do the problem. Okay, I'm going to assume that you did the problem, and now you're going to check your answer. So the problem says the diffusion rate of an unknown gas is measured and found to be 31.5 milliliters per minute. Okay, now that's great units for a rate. How many milliliters travel per minute? Okay, some kind of distance or some kind of amount per unit time. Under identical experimental conditions, the diffusion rate of O2 is found to be 30.5 milliliters per minute. These are my choices. What is the identity of the unknown gas? That's one of the major uses of Graham's law. It's for identifying unknown gases, okay, by comparing their rates of diffusion, okay? So let's see how this works out. So basically 31.50, okay, that was the rate of my unknown. So it goes down here, okay? And this guy was my rate of the oxygen. So this is rate 2, and it's going to go with the oxygen up here. Got to make sure you get that straight. Now, what's the best way to solve this? Definitely cross-multiplying, okay? So if I was going to punch this into my calculator, it would look a little something like this. I would take the 30.50, multiply it by the square root of 32, right? This times this, and then it would be equal to this times this, right? Okay, and to get the square root of the unknown by itself, I divide both sides by 31.5, okay? But this is the part people always forget. Now you got the square root of this unknown molar mass. So to get rid of that square root, I have to square both sides. Okay, so this ends up getting squared, and my answer is about 30, okay, grams per mole. Well, if you look at the molar mass of each one of these cute little compounds, okay, so adding them up off the periodic table, the best match is NO. So the answer is no. I mean, yes, it is. I mean, no. I mean, yes, it is NO. Okay, so did you get that right? All right, good. We're almost done here. All right, so next order of business. Let's see. Well, you know what? There's gaseous diffusion, and then there's effusion. Many of you guys asked about that in your summer work. Well, heck, you know what? They're exactly the same thing, except effusion is basically when you release a gas, but you do so in a vacuum, so you don't have the interference from air. Diffusion is basically when you release a gas, but it has to travel through air. Okay. So that's basically the difference. Gaseous effusion tends to be much more accurate because you don't have that air interference, okay? But the relationship is exactly the same. So take a look at this problem. So just calculate the ratio of the effusion rates, same thing as diffusion really, of hydrogen gas and uranium hexafluoride, a gas used blah, 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 okay? So here we're going to basically use Graham's law again. So here's where I'm going to pause, and I want you to try it, and then resume the video to check your answer. Okay, let's see how you guys did. Now, one tip that I definitely want to give you is that if you want the ratio of the rates, right, you want that ratio to be like a whole number, okay? So that's why I put the hydrogen on top, because is hydrogen or is uranium hexafluoride going to travel faster? Hydrogen's really tiny, so its rate is going to be really fast. Okay, so that's why I put that guy on top. So if your answer came out to like a decimal, it's probably because you just want to kind of flip everything. Okay, so here's my rate of hydrogen compared to the rate of uranium hexafluoride. Okay, and then I made sure the hydrogen went down here and the uranium hexafluoride went up here. Okay, did the math, came out to 13.2. So that means uranium hexafluoride fuses 13.2 times faster than hydrogen. Makes total sense since uranium hexafluoride is super big. Okay, travels very slow. Whoops, you know what? I had that totally backwards. Please correct that. Oh my gosh. So what does that really mean? Hydrogen fuses 13.2 times faster than uranium hexafluoride. Whew, glad I caught that. Sorry about that. All right, you guys, you know what? I gave you one last problem. This one's a little bit trickier. It says the time required for a volume of unknown gas to effuse through a pinhole is 71.5 seconds. The time required for the same volume and same temp and pressure of oxygen is 63 seconds. So again, we're basically comparing something that is known to an unknown, okay? And again, we'll be able to figure out the molar mass. The key that's different here is notice the information I gave you. I gave you time. So my question to you is time the same thing as rate? Well, gosh, let's see. If you're going from your house to school and you're going 90 miles an hour, right? That's a really fast rate, a really high rate. Well, you're going to get here super fast, right? So you're going to get here in a really, really low time, right? It's only going to take you like 1 minute to get here. So you know what? They actually have an inverse relationship. Okay, so a low time, meaning like quick time, is a fast rate, right? A really big rate. Okay, you're covering a lot of distance or you're producing a lot of volume per time. So, how do we handle this? Well, the bottom line is do it a couple different ways. Okay, what I would suggest is you guys give it a try and then check the answer key. Okay, if you just remember that this time, okay, is really inversely related to rate, you might set it up like this. Say that, oh, okay, well, you know what? I'm going to produce this amount, whatever it is, in 63 seconds. For the other one, I'm going to produce this amount, but in 71.5 seconds. So it's kind of like an amount per unit time, an amount per unit time. Okay, so you can sort of make that look like a rate. Okay, well, from there, you know what? It's going to be the exact same. Make sure that this corresponds to oxygen, so it went on bottom. This corresponds to the unknown, so it goes on top. Okay, so you can basically solve, again, I would definitely cross multiply, be really careful with your math. Okay, and the answer comes out to 41.2 grams per mole. All right, another relationship, just another way to twist this around is that, rate is inversely proportional to molar mass, right? Like a really fast rate means that it's you know what I mean, a really heavy molecule, okay, is going to travel a slow rate, a low rate, right? Inversely related. Well, when it comes to time, well, it's exactly the opposite, okay? If it takes a really, really, really long time, okay, so a big time, then that's going to correspond to a big molar mass, okay, because it's going to be a big, huge, slow guy, okay? So you can actually create a direct relationship here, and you're welcome to use that, okay? But either method works. So, and we'll do some more examples like this in class. Well, thank you very much for listening. Please let me know if Ms. Schneider and I can make these better. I'm sure you have lots of suggestions. And of course, if you have questions, we'll take them in class, okay? But other than that, thanks for listening, and we'll see you tomorrow.